Right, so in this video what I'm going to do is show you an alternative way of figuring out the nature of stationary points. And this is really important for all Year 13 work. If I just draw you some sketches, if I show you a local max point, and I'll show you a local min point, then I'll show you a point of inflection, like so. But remember, a point of inflection could go the other way, so I'll just exaggerate it and put it like so. Now, if you notice what is going on in each of these pictures, let's take the local max first. If I take a point just slightly to the left-hand side, so if this was an x-axis, like so, and that might be a reading, I don't know, for example, of 2 on the x-axis for that point there. At x equals 2, we'd say there's a stationary point. Now, if you were to just go slightly less on the x scale, slightly below it, I don't know, say 1.9, something like that. Okay, and looked at the gradient of that point there, if I draw a tangent there, you'll see that the gradient of that tangent is a positive because it's a positive slope. Likewise, if I was to go slightly further along the x-axis to say 2.1 on that scale, so we've got a point just a bit further along the x-axis on that curve. If I was now to draw a tangent at that point there, like so, you can see that the slope is negative for that tangent. So when you are following the gradient as you go through a local maximum, the gradient as the x numbers get bigger towards the stationary point go from being positive. At the actual stationary point itself, the gradient is 0. And then as it carries on along the curve and as the x numbers get bigger along the scale, the gradient flips to being negative. So this is the sequence that we see for the gradients in the region of a local maximum. The gradients go positive, 0 at the stationary point, and then turn negative. That's really important. If you do the same sort of idea here, at the stationary point the gradient obviously will be 0. Slightly smaller x numbers lie to the left, so say there, if I draw the tangent there, it's a negative slope. And if I make the x numbers slightly bigger, so say up here, then the tangent is a positive slope. So for a local minimum, the slope goes negative, then 0, then positive in the region of the stationary point, which is a local minimum. The same sort of idea can happen for this type of point of inflection. At the point of inflection itself, the slope is 0. But if I make the x values slightly smaller, say in that position there, then that slope is negative. And if I make the x numbers slightly bigger, say in that region there, you can see that the tangent also has a negative slope. So in this particular example of a point of inflection, the slope values go negative, 0, negative. So negative, 0, negative in the region of the stationary point for the slopes. And then finally, if you have this type of point of inflection, again at the point of inflection the tangent would have a 0 gradient. Slightly smaller x numbers to the left, draw the tangent. That tangent has got a positive slope. Make the x numbers slightly bigger, draw the tangent, and you'll find that the slope is again positive. So for that type of stationary point, the gradients go positive, 0, positive in the region of the stationary point. And these 4 different patterns of gradients are critical in evaluating what type of stationary point we've got. So if I now refer back to, I'll turn over the page to a question we did on the previous video, whereby, let me just remind you, I took y equals x to the power 4 and we worked out by the derive by dx equals 0 techniques that there was a stationary point at 0, 0. We worked out the second derivative, we found it to be 12x squared, and at x equals 0, we worked out that the second derivative was 0. Now in the past we would have thought that was going to be a point of inflection, But I've now said to you, we know what the y equals x to the 4 graph actually looks like. It looks like that, which is a local minimum. So that is quite clearly not right. And I did say in the last video, d2y by dx squared equals 0 is not automatically a point of inflection. It's what we call ambiguous. It could be a point of inflection. It's the only scenario which could be a point of inflection, but it doesn't have to be. It could still be a local max. It could still be a local min. So what I've got to do to identify this completely, okay, if d2y by dx squared, for example, turned out to be positive, I know for sure it will be a local min. There's no ambiguity. If it turns out to be negative, I know for sure it's a local max. But if it turns out to be 0, which is what we've got here, it's an ambiguous case. So this is what I've got to do now. I've got to make use of what I said over here about points of inflection and max and min, the gradients of these pattern gradients. So what I'm going to do is work out for the point 0, 0 at x equals 0, I'm going to now look at dy by dx values, the gradient in the region of x equals 0. So I'm going to let's make the values slightly smaller. So x equals minus 0.1, for example, which is slightly smaller than 0. At x equals minus 0.1, let's go back to dy by dx. dy by dx will work out to be 4 lots of minus 0.1 cubed. Well, you don't have to work this out because it's obvious. If you cube a minus, you get a minus, and then times it by 4, you get a negative. So minus 0.1 gives you a negative dy by dx. Let's now go the other side of x equals 0, make it slightly bigger, plus 0.1, and we'll work out dy by dx for that. dy by dx will be 4 lots of positive 0.1 cubed. Well, this thing here, if you work it out, must obviously be a positive quantity. So what we're seeing is, if you just now consider what's going on in the region of the stationary point, which is 0, 0, I know that the gradient goes negative, and then at the stationary point itself, it will have a slope of 0. So at x equals 0, dy by dx is 0, and then as x gets bigger, dy by dx goes positive. So it's a negative 0 positive pattern, which if I just flip this over to what we looked at earlier, it's negative 0 positive pattern, which means we must have a local minimum situation. So that is the reason why when I now do the sketch, I do the sketch like so. There is the stationary point at 0, 0, and it could have been a point of inflection when we did that. But by doing this technique here, I can see actually it's not. It must be a local minimum. And the picture looks like that. So this idea of working out dy by dx to see the pattern of the gradients is critical in this situation to overcome the ambiguity that d2y by dx squared equals 0 gives us. That's the end of this video.